Good morning, students. So today we'll continue with the previous chapter, Haloalkanes and Haloarenes. Okay. So are you able to see the PPT? The screen is clear? Okay, thank you. So we'll start. So last class we were discussing about substitution. Yes, substitution nucleophilic reaction, right? So we had discussed about the SN1 mechanism, right? So SN1 mechanism, the reaction, it proceeds via two steps. Okay. So the first step, it is a slow step. It leads to the formation of carbocation. So this is carbocation. So as you can see in tertiary butyl halide, it is so this bond, okay. So here, so this CX bond, okay, CX bond, it is a polarized bond. Okay, so this is a polarized bond. So this is highly electronegative atom. So highly electronegative atom, what it will do? It will tend to pull the electron towards itself. So as a result, this will be partial negative, this will be partial positive. Okay, so as a result, this X, that is halide group, when it is leaving, it will take it electron pair with it and it will leave. Okay, so as a result, this carbon, it will be left, it will be electron deficient and it will have a positive charge. So it is carbon is having a positive charge. Thus, it leads to the formation of carbocation. So this is tertiary butyl halide. So this is a tertiary carbon. Okay. So this is a tertiary butyl halide. It undergoes a slow step. So first step is a slow step. Okay. It undergoes the formation of carbocation. Next. Second step is what? Second step is a slow step, and this second step is a fast step. So here, whatever the carbocation is formed, the carbocation formed here in the first step is taken, and what is done? Your nucleophile, okay, nucleophile, that is OH minus, it will attack your carbocation and it undergoes a fast reaction, and thus formation of tertiary butyl alcohol takes place. Okay. So the first step, which is the formation of carbocation, it is a slow step and it is called as the rate determining step. So rate of this reaction, it depends upon the concentration of only one substance, that is your substrate. It depends upon the concentration of substrate only. Okay. So the order of reactivity of alkyl halide is what? It depends upon the stability of carbocation, how the formation of carbocation takes place. So it depends upon the stability. So the stability, it is tertiary carbocations are more stable than secondary, and then is your primary. Okay, so tertiary carbocations are more stable, then secondary carbocation, then primary in which mechanism? In SN1 mechanism. Okay, remember this stability. Okay. So then it may be noted that in case of optically active alkyl halide, so we'll see what is optically active alkyl halide in our further discussion. So optically active alkyl halides that of SN1 reaction, it results into racemic mixture. Okay, racemic mixture means retention and inversion. Okay, so retention and inversion, so plus and minus. So what happens? Plus and minus, it cancel each other, and it is called as the mixture. Okay, mixture of retention and inversion, it forms a racemic mixture. So 50%. So in case of SN1 reaction, it shows 50% retention, 50% inversion. So thus it is called as racemic mixture. So these are the things you need to remember for your SN1 reactions. So next we'll go for SN2. So what do you mean by SN2? SN2 is substitution nucleophilic, okay, bimolecular. Bimolecular means what? Here the rate will depend upon two substances. Okay, so we'll see. So this is the so this occurs in one step. So SN1 reaction, it occurs via two steps, and in SN2 reaction, it occurs via one step. Okay, so here the starting reactant taken is methyl halide. Okay, methyl halide is what? CH3X, right? Methyl halide. So CH3, they have just written a complete structure. So CH3X, it is a methyl halide, is your starting reactant. So what is done? Nucleophile Okay, so nucleophile attack. So how does the nucleophile attack? Nucleophile will attack from the rear side. Okay, this is the front side. This is the front side. So I'll represent the front side with the red. Okay, so this is the front side, and with the purple color, this is your rear side. So what happens? Nucleophile will attack from your rear side of the carbon. So that is rear side is back side of the carbon. The attack will takes place. So what will happen? So here the partial formation of this, here you can see, okay, it forms a transition state. What do you mean by transition state? Here carbon will have 5 pentavalency. Okay, carbon, you know, it should have tetravalency, but it so it forms a pentavalency. Pentavalency means what? Carbon is unstable. Okay, it undergoes a transition state wherein formation of bond between this OH and C. So this is the formation of bond taking place. So there is making of this OH-C bond and breaking. Okay, simultaneously, if this bond OH is attacking on C, so it is making of this bond takes place and breaking. Okay, simultaneously it should break. Why it should break? Because carbon will not have pentavalency. It should have what? Tetravalency. So this bond will break. So this bond will break. So making and breaking of bond takes place simultaneously. So it undergoes a transition state. Why? Because this carbon is unstable. Why it is unstable? Because it is having a pentavalency. Okay, pentavalency means 5 bonds are formed. So making and breaking of bond takes place simultaneously. Thus it undergoes a transition state. So this will leave, okay, and it forms this product, that is methyl alcohol. So it occurs via one step. Okay, it occurs via one step, methyl halide. So the nucleophile will attack from the rear carbon. Then it undergoes a transition state wherein making and breaking of bond takes place simultaneously. As the carbon is unstable, it is having a pentavalency. Okay, so it undergoes a fast step. So this is a very fast step. So this halogen halide leaves and it forms a methyl alcohol. Okay, so this is your substitution nucleophilic bimolecular. Here the rate of the reaction, okay, the rate of the reaction depends upon the two substances. One is your substrate and one is your nucleophile. Okay, it depends upon the substrate and your nucleophile. So your rate concentration, it depends on both, that is your nucleophile as well as the substrate. So the nucleophile, so here attacks from the opposite side to that containing the halogen atom. So the rate of the reaction is directly proportional to the concentrations of both nucleophile and substrate. Wherein the case of SN1 reaction, the concentration, it depends, the rate of the reaction is directly proportional to the concentration of only substrate. Here it depends upon the nucleophile as well as the substrate. Okay, so this is about SN2 mechanism. So how is the order of reactivity? The order of reactivity is the SN2 mechanism is primary carbocation is more stable, then secondary carbocation, then is your tertiary. So in case of SN1, it is tertiary is more stable, then secondary, then primary. In case of SN2, it is primary is more stable, then secondary, and then your tertiary. So remember this, okay? Now, why is it so that primary tertiary is not so stable in case of SN2 mechanism? See here, I'll tell you what is the reason why tertiary is not more stable in case of your SN2. Okay, SN2. In SN1, tertiary is more stable, but why it is reverse? Okay, in case of SN2. Because what happens in this particular nucleophile will attack from the rear carbon. You see, these are very bulky groups, right? CH3 methyl groups are very bulky group. I can illustrate this in much more. So CH, okay, I can write the complete structure, then you will get to know. So these CH3 molecules, they are bulkier groups. Okay, they are bulkier group. Thus the attack, so to attack the nucleophile from the rear carbon. So there is steric hindrance. Okay, there is steric hindrance around this carbon. Okay, so it is not possible for the attack to take place. Thus primary, in case of primary, how it will be? Okay, there are hydrogen atoms. So nucleophile can easily attack the rare carbon, right? In this case, it is not possible. Why? Because there are bulkier groups, methyl groups are present. So there is steric hindrance. So remember the word steric hindrance. So in case of optically active alkyl halides, so okay, so whenever you are discussing about optically active alkyl halides in SN2 reactions, so it undergoes inversion. Okay, in case of SN1, it undergoes what? Racemic mixture, that is 50% retention, 50% inversion. Okay, so in case of SN2 mechanism, it undergoes inversion. Okay, complete inversion of mechanism. What do you mean by inversion? I'll show you. So here you can see, okay, in this reaction, you can see how is this, okay. You can see here okay, so your H bonds are here, okay, and halide group is here. So here you can see the, okay, you can see the inversion. The halide group is leaving from here. The attack is taking from the back side. So it is complete inversion, right? So this is said to be inversion. Okay, retention means the molecule, how it is in the starting reactant, it will be in the same position. Only the leaving group will be replaced by the nucleophile. So this is inversion and retention. So next we'll discuss some of the questions. The order of reactivities of the following alkyl halides for a SN2 reaction. Yes. What is this? Yes. So it is D. The correct answer is D. Why it is D? Why it is D? Because with the decrease in size of the halides, okay, with the decrease in size of the halides, the CX bond, what will happen to the CX bond? What will happen to the CX bond? That is the CX bond energy will increase, right? So, and the reactivity of alkyl halide will decrease. So, as you go down the group, the nuclear charge will be more in the bulkier groups. Okay, so we have discussed this. So this is so the answer is D. Option is D. Tertiary alkyl halides are practically inert. Okay, alkyl halides are practically inert to substitution by SN2 mechanism because of why it is tertiary alkyl halides are more stable. Tertiary alkyl halides are practically inert to substitution by SN1 mechanism. Okay, means what? Why tertiary alkyl halides are not much this towards SN2 mechanism? Tertiary alkyl halides, we had discussed this. Tertiary alkyl halides are not that stable as compared to how is the in SN2. How is the reactivity? Primary is more stable than secondary and then tertiary, right? Now, when you're discussing, they said tertiary alkyl halides are practically inert, okay, to substitution by SN2 mechanism because of D, steric hindrance, right? Because of steric hindrance, tertiary alkyl halides, they are practically inert. Say, okay, so this is the correct answer. Steric hindrance. We had discussed steric hindrance. Answer is D. Okay, steric hindrance. Which of the following is the correct order of decreasing SN2 reactivity? Yes, SN2, which is more stable in SN2? Primary is more stable than secondary and then tertiary. So here, which you can see it is primary carbon. A, right? R. You can see the R. R, only one, then R2, then R3. Okay, so this is with respect to, so primary is more stable than secondary and then is your tertiary. So it is A. Okay. SN2, remember in SN2, primary is more stable than secondary and then tertiary. And for SN1, tertiary is more stable than secondary and then your primary. Next, the organic chloro compound which shows complete stereochemical inversion during a SN2 reaction is, yes, So these are some of the compounds given. So the organic chloro compound, which will show complete stereochemical inversion during SN2. So in SN2, again the order primary, secondary, and tertiary. So which will show you a complete inversion? Primary. So in this, which is the primary? It is A, right? Correct. CH3Cl. CH3Cl is a primary. Okay, so this is tertiary. This is secondary. This is secondary. So this is a primary. A. A is the correct answer. So remember this. Okay, stereochemical inversion is shown by primary alkyl halide. Okay. A solution of -1 chloro, 1 phenyl ethane in toluene racemizes. What do you mean by racemizes? Slowly in presence of a small amount of SbCl3 due to the formation of. When do you form racemization? When do you form racemization? In which mechanism does racemization takes place? In SN1, right? In SN1. So SN1, what does it forms? It forms carbocation. So it is D. Okay, the correct answer is D. The correct answer is D because it leads to the formation of carbocation. Which one of the following is not true for hydrolysis of tertiary butyl bromide with aqueous ammonia? Tertiary butyl bromide. Tertiary butyl bromide means CH3, 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 Br. Okay, tertiary butyl bromide with aqueous ammonia, right? Aqueous ammonia. So OH is the nucleophile. So it reaction occurs by SN1 mechanism. Correct. Okay, this is correct. So we have to see which is not true. Okay. The intermediate formed is a carbocation. So this is also correct. Then rate of the reaction doubles when the concentration of alkali is doubled. Does it depends upon the concentration of alkali? Does it depend upon the nucleophile? No. So this is wrong. So this is wrong. Okay. So the correct answer is C. The correct answer is C. Okay. The rate of the reaction, it depends on what? It depends only the concentration of the substrate. So this is also correct. So the correct answer is C. C is the correct answer. Okay. Then optical isomerism. Okay. Optical isomerism. The conditions for the presence of optical isomerism is. Now, when do you say that it is optically it is optical isomer? Okay, so the compound when you have a chiral, what do you mean by chiral center? Okay, what do you mean by chiral center? Whenever the carbon, okay, it is having 4 different atoms attached to it. Okay, when it is having 4 different carbons attached to it, it is said to be a, it is said to be what? Chiral. Okay, it is said to be chiral. Okay, whenever the compound, so take an example of this particular compound. So whenever this carbon, so this carbon is having 4 different group attached, right? So then it is said to be a chiral. It is said to be chiral. When, okay, or it is said to be asymmetric carbon. When it is said to be asymmetric carbon or chiral, that is when carbon atom should be linked to 4 different group atoms. Then when it is said to be achiral, achiral means what? CH3, H, H, okay, COOH. So are in this, is all the groups different? No, right? These are same. So this is said to be achiral. Okay, when the carbon atom is not linked to 4 different groups, then it is said to be achiral. Chiral means what? When the carbon atom is linked to 4 different groups, or it is said to be asymmetric carbon. Okay, so it is the condition for optical isomerism. Then second is what? Mirror images must be non-superimposable. What do you mean by non-superimposable? Okay, now our palms. Okay, now the when you hold this, okay, like this. So these are what? These are mirror images. Okay, if you keep both the hands in front of each other, what happens? So they are mirror images. Now this mirror images should not be superimposable. Now you, what you do? You keep your one hand on the another. You see, are your fingers coinciding? No, right? Your thumb is coinciding with your little finger, right? So it means what? mirror images must be non-superimposable. So then if non-superimposable mirror images are there, then they are said to be enantiomers. So two conditions, it should be chiral and the mirror images must be non-superimposable. Okay. So for the molecule to show optical isomerism, these are the two conditions. One should be, it should be chiral or it should be asymmetric carbon, and second, it should be that the mirror image should not be superimposable. It should be non-superimposable. Okay. So these are the conditions for optical isomerism. Now we'll see chiral carbon. What do you mean by chiral carbon? So the carbon attached to 4 different groups. Okay. The carbon attached to 4 different groups. Then it is said to be 4 different groups or atom is said to be a chiral carbon. So here you can see the example. Okay, C. So this carbon is said to be a chiral carbon. Why? It is attached to 4 different groups. Okay, and this 4, if you place a mirror, on this particular image, okay, what will happen? Will it coincide on this? No. Right, CH3 will coincide on this? No. So these are non-superimposable mirror images. So these are called as enantiomers. Okay. So this is dextrorotatory. This is levorotatory. What do you mean by dextro and levorotatory? This will dextrorotatory. It will turn the plane polarized light to right side. Okay. When the plane polarized light is turned to right side, then it is said to be dextrorotatory. When plane polarized light it turns it to left side. Okay, if it turns the plane polarized light to left side, then it is said to be a levorotatory. So the carbon, if it is attached, so for the molecule to show optical isomerism, first it should be chiral. So this is the chiral, and when you place a mirror, you can see CH, this molecule will not coincide on this, so it is non-superimposable mirror images. So when it is non-superimposable mirror images, then it is said to be a enantiomers. Next, racemic mixture. What do you mean by racemic mixture? It is an equimolar mixture of 2 enantiomers. Okay. It is an equimolar mixture. It is a equimolar. Equimolar mixture means what? 50% of plus and 50% of minus. Okay. Okay, that is 50% plus and 50% minus. That is equimolar mixture of 2 enantiomers is called to be racemization. That is what this will plus and plus, this will be 0. Okay, so this is 0. It is 0 optically active. Then it is said to be racemic mixture. When, for example, when equal amounts of plus lactic acid and minus lactic acid are mixed together, we get plus minus lactic acid. So this is the example for racemic mixture. So racemic mixture is always optically inactive. Okay, so racemic mixture is always optically inactive. Okay, it is optically inactive. So mesoisomers, what do you mean by? Next is mesoisomers. Molecule containing chiral carbon atom but having plane of symmetry in the molecule is called as mesoisomer. Okay. Now molecule containing chiral carbon atom. Now you can see this molecule. Okay, the given molecule down here. So this is a carbon which is having different. Okay, this is one atom. This is another atom. This is another third atom, and this is another third atom. So this is said to be a chiral carbon. With respect to this, if I talk about this second carbon, this is one atom. This is second. This is third, and this is fourth. Okay. So so this is also chiral. So molecule containing chiral carbon atom. So this is satisfied. Okay, but having plane of symmetry. Now, what do you mean by plane of symmetry? Okay. So what do you mean by plane of symmetry? Now, if you keep a mirror image, on this here, what will happen? This molecule will coincide on the other, right? So the upper molecule will get coincide on the down molecule. So this is said to be mesoisomer. So that is what molecule containing chiral carbon atom but having plane of symmetry in the molecule is called as mesoisomer. Okay. So this is example of tartaric acid. Tartaric acid, it is optically inactive. Okay, it is optically inactive. So this is getting cancelled with this because of plane of symmetry. So this is called as mesoisomer. So it is containing chiral carbon atom, but it is having what? Plane of symmetry. So which one of the following compounds is not chiral? So you have to write the structures and tell me which one of the following compounds is not chiral. Not chiral means what? It is achiral. Okay. That is, it is not having four different this atoms attached to it. So I'll write the structures. You tell me CH2, 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 CH3. This is what your A. Okay, then B, CH3, then 2-chloropentane, right? CH3, CH, then chloro, 2 at 2 positions. So it is 1, 2, 3, and 4, 5. Okay. Then C is 1-chloro, 2-methyl pentane. So it will come like this. C H CH3 CH2 CH2 CH3. Okay. Then the D CH3 CH CH3 CCl H CH2 CH3. Yes, can you tell me? So this is a chiral. Okay, I'll just mark it with another color. You can see. So this is chiral. This is chiral. So just see which is not chiral. So allow around this also. So this is one. This is second. This is another. So around this also you have a chiral carbon. In this case, do you have a chiral carbon? No. So it is A. The option is A, right? Yes. Yes, correct. A is the correct answer. So like this, you have to see, okay, around the carbon atom, you have to check whether you have different atoms attached to it or no. So in A, there is no chiral carbon. Okay, so it is hydrogens. You can see here. These are hydrogen atoms, right? So these are same, right? So it is a chiral. Correct. Yes, A is the correct answer. So we'll go for the next question. Which of the following has a mesoisomer also? Which of the following will have a mesoisomer also? Mesoisomer. Mesoisomer, it should be chiral carbon, but it will have a plane of symmetry. Okay. It should have not, it should not have, no, it should have a mesoisomer. No, not the D, not D. D is not the correct answer. Yes, yes, Lohit, correct. It is B. Yes, yes, it is B. Okay, I'll write the structure of 2,3-dichlorobutane. You can see C, okay, Cl, then CH3, C, okay. So this is what? 2, 3. You can see here. Butane, right? 1. I'll just name it with another, take another color here. So 1, 2, 3, 4. Right? So it is 2,3-dichlorobutane, right? So it is, so if you keep a mirror here, so it is a mesoisomer. Okay, so this is the correct answer. So B is the correct answer. Good. Many have answered. Good. Okay, so we'll move for the next question. So out of the following, the alkene that exhibit optical isomerism. Yes, for a molecule or for compound to show optical isomerism, what are the condition? First condition is it should be having a chiral carbon. Second condition is what? They should be mirror images should be non-superimposable. Okay, they should have non-superimposable mirror images. Yes, you have to be quick in writing the structures. Okay, first you need to write the structures and then you have to justify. No, not B, not B, no. Yes, again Lohit Kumar. Yes, correct. Yes, it is A. Okay, it is A. So how it is A? How it is A? Just see the structure. Just see the structure. CH2 CH, C, CH3, H, CH2, okay, CH3, right, pentene, right, the structure is 2, the structure is what? 3 methyl, okay, so it is 1, 2, 3 methyl, 1 pentene. Just a second. Okay, so 1, 2, 3, 4, 5. Okay, so 3 methyl, 1, okay, here 1, this is pen, and it is in pentene. So it will exhibit a optical isomerism. So this will show you optical isomerism. Okay, so we'll go for the next question. How many chiral carbon atoms are present in 2,3,4 trichloropentane? Yes, write the structure of trichloropentane, pentane. So it should be 1, 2, 3, 4, 5, right? So 2, 3, 4. Okay, at second, third, and fourth, you have your Cl. Right, then this will be CH3, this will be CH3, this will be H, H, H. Yes, tell me how many chiral carbons they have? Let me see who has answered it correctly. Yes, many have answered C. C is the correct answer. Okay. Yes, I'll explain. See here. Around this carbon atom, 1, 2, 3. And this is the next. Okay. Fourth atom. So this is 1 chiral. So this is 1 chiral, right? So this is correct. Now, I'll just erase this. Okay. Understood? 1. Now, second, we will see this. If you want to see this, okay, 1, 2. So this 3 and this is same, right? This is same. So this is not chiral. So this is not a chiral carbon atom. So, okay. So only which is a chiral atom we found? First one. Now we'll see with respect to this. So 1, 2, 3, and the next one. So this is, okay, understood now. So there are 2 chiral carbon atoms. Okay. So there are 2 chiral carbon atoms. The correct answer is C. Yes. Many have answered C. So this is the carbon. What do you mean by carbon? Chiral carbon is around the carbon atom, all the attached carbon atoms. Okay. Attached atoms should be different. Here, whatever the carbon, here you can see, right? So the attached atoms should be different. So hydrogen is different, chlorine is different, CH3 is different. Around this carbon, you have to see the other atoms. So this is a different atom. Okay, this is a different. So the around the carbon atom, if there are 4 different atoms, then it is said to be a chiral. So we'll go for the next question. Say you have another. The number of optical isomers of the compound CH3, CHBr, CHBr, COOH is. Okay. So write the structure. So it is CH3, CHBr, okay, CHBr, then C double bond OH. Okay, so number of optical isomers you can calculate how? How you can calculate optical? Yes, Chandru, correct. It is D. We'll see. Okay, we'll see how it is D. So you have to calculate the number of optical isomers by 2 into N. N represents your number of asymmetric carbon atoms. Asymmetric carbon atoms means what? Chiral atoms. So first you have to see the chiral atom. So here the chiral carbon is, these are the 2 chiral carbons. Okay, these are the 2 chiral carbons. So you can see here how it is 2 chiral carbons. So this is 1, 2, 3, and this is another group. Okay, then I'll check with the other pen. So this is with respect to this 1, 2, then this is third group, and this is the fourth. Okay, so this is correct. So this is what? This is having two chiral carbons. So this is having two chiral carbons. Okay, so 2 raised to 2. 2 raised to 2 is what? It is 4. So number of optical isomers are 4. The answer is D. Answer is D. So whenever you want to calculate the number of optical isomers, it is given as 2 raised to n. N is nothing but number of chiral centers. Okay, remember this. Next, meso compounds do not show optical activity because. Why they do not show optical activity? Why they do not show optical activity? What do they contain? What do they contain? Why is the optical activity missing in meso compound? No, they contain chiral carbon atom. Yes, the correct answer is C. Yes, Parvati, correct. Irapura, it is correct answer. It is C. Okay, they contain plane of symmetry. Correct. Good. Okay, so they contain plane of symmetry. So because of that reason, okay, because of that reason, meso compounds, they do not show optical activity. So next we'll start with the aryl halides. So you know what are aryl halides, right? So one of the hydrogen atom is being exchanged by, or it is replaced by halogen. Okay, and this halogen atom is linked to the carbon which is sp2 hybridized. Okay, sp2 hybridized. So in this compound, the halogen is linked directly to the carbon of the benzene. Why it is benzene? Because it is aryl halides. Okay, in benzene you have what? sp2 hybridized carbon. So first is electrophilic substitution. So you can see this is the reaction of electrophilic substitution. Toluene plus X2. X2 means what? It is undergoing a halogenation reaction in the presence of Fe in dark condition. The condition is dark. Okay, you get ortho-halotoluene and para-halotoluene. Okay, so this is ortho position. With respect to your toluene, that is your CH3 group, it is here. So it is ortho. Okay, and when it takes the opposite sign, so like this, okay, with respect to this, it is called as para. So whenever you want to form ido, okay, this is with respect to halogenations. So ido derivatives cannot be obtained by direct reaction with iodine. Why? Because the reaction is reversible. So the reaction is given here. So if you want to do iodination, okay, so it is reversible. Again, you will get this particular starting product. So ido derivatives cannot be obtained by direct reaction with iodine because it is the reaction will undergo reversible reactions. So, okay, ido derivatives can be prepared. How they can be prepared then? They can be prepared by reactions which is carried out in the presence of oxidizing agent. So it can be carried out in the presence of oxidizing agent. So what is the role of oxidizing agent? Oxidizing agent will oxidize your hydrogen iodide to iodine. Okay, hydrogen iodide, it can be oxidized to iodine. So your here Hi plus HNO3 gives you nitro group, water and I2. Okay, so what is happening here? Hi is being reduced. So which is the oxidizing agent here? HNO3. Oxidizing, it is a good oxidizing agent. So what it is doing? So it is reducing, it is oxidizing your Hi to iodine. Okay, it is oxidizing from -1, it is undergoing 0 oxidation state. So it is oxidizing. So HNO3 is a good oxidizing agent. So aryl fluorides. So whenever you want to form fluorides, okay, fluorides, they cannot be prepared by direct fluorination. What is the reason? Because fluorine is highly violent. Okay, whenever, so because of the high affinity of fluorine for hydrogen and the reaction is very violent. So this is a reason why we cannot prepare alkyl fluorides, because the reactivity of fluorine, the affinity of fluorine to hydrogen is very high and thus the reaction is very violent. Okay. From diazonium salts, important, how do you prepare diazonium salts? So this is aniline. So this is the aniline. So aniline is taken. So aniline is taken. So aniline is taken here. So aniline is treated with NaNO2. Okay, sodium nitrite solution in the presence of HCl and condition is 0 to 5 degrees Celsius. Okay, 0 to 5 degrees Celsius. So NaNO2 plus HCl at 0 to 5 degrees Celsius, it forms benzene diazonium chloride. Okay, it forms benzene diazonium chloride. So it forms what? Benzene diazonium chlorides. Okay. So if you treat this benzene diazonium chloride with CuCl, okay, if you treat it with CuCl, you get what? C6H5Cl. How this Cl is replaced? This Cl is replaced from the CuCl. Okay, your C6H5Cl, what you get, the substituted product, that will be replaced by your CuCl. Okay. So this is called as Sandmeyer's reaction. This is called as Sandmeyer's reaction. So if you write this complete structure, that is from aniline, if you treat it with NaNO2 in the presence of HCl and 0 to 5 degrees Celsius, you get what? Benzene diazonium chloride. This benzene diazonium chloride further reacted with cuprous chloride gives you C6H5Cl. This is called as Sandmeyer's reaction. With respect to, if you want to prepare a substituted product on benzene as Br, okay, if you want to form benzene, this bromobenzene, then what you have to take, instead of CuCl, you have to treat it with CuBr. You have to treat it with CuBr. Okay, you have to treat it with CuBr. So then, so this is also an Sandmeyer's reaction. Then, if you treat this benzene diazonium chloride with Ki, potassium iodide, you get what? Iodo product. Okay, you get C6H5 iodine. Okay, iodide, C6H5 iodide. So then it is said to be C6H5I. So this is what? So this is also a substituted product of iodine you get. So next, if you treat this benzene diazonium chloride, if you treat this benzene diazonium chloride with HBF4, okay, HBF4, then you get C6H5F. So fluorine will be the substituted product on benzene. Okay, you get fluorobenzene. This is called as Bals-Siegmann reaction. Okay, this is called as Bals-Siegmann reaction. So with benzene diazonium chloride, further reaction with HBO4, okay, you get it fluorobenzene. So that is Bals-Siegmann reaction. Then if you treat the benzene diazonium chloride with copper powder plus HBr, okay, you get fluorobenzene. This is called as Gattermann reaction. So this is called as Gattermann reaction. Okay, this is called as Gattermann reaction. Yes. So this is called as Gattermann reaction. So first is your Sandmeyer's reaction. So first is your Sandmeyer's reaction. Okay, with cuprous chloride and cuprous bromide, you get Sandmeyer's reaction with HBO4 on with treated with benzene diazonium chloride. You get what? Bals-Siegmann reaction, and copper powder plus HBr, you get Gattermann reaction. Okay, remember this name reaction, very important. Okay, so based on this, we'll solve some questions. The reaction of toluene with chlorine in the presence of ferric chlorides gives predominantly. Okay, so what is the reaction? Yes. So the reaction of toluene, what is the answer? How we will solve this? So the reaction of, I'll write the reaction. So when you treat the toluene with chlorine, okay, when you treat your toluene with chlorine Cl2 in the presence of ferric chloride, it gives you what? It gives you, the answer is what? D. Okay, the answer is ortho-para-chlorotoluene, right? We had seen this. So, with respect to this, you will get plus CH3 ortho para chlorotoluene. Yes, correct. Okay. So it is D. Yes, most of you have answered correct. So we'll go for the next one. Decomposition of benzene diazonium chloride by using Cu2, Cl2, HCl to form chlorobenzene is. Yes, what is the name of the reaction if you take Cl2 plus HCl? A. Yes, Sandmeyer's reaction. Yes, correct. Good, good, good. Okay, Sandmeyer's reaction. Next, Friedel-Crafts reaction of bromobenzene with methyl iodide gives. Friedel-Crafts. What do you mean by Friedel-Craft on bromobenzene? Okay, so now bromobenzene, bromo, Br, okay, bromobenzene plus methyl iodide. So this is methyl iodide in the presence of Friedel-Crafts reaction. How it goes? AlCl3. Okay, this is Friedel-Crafts reaction. How it forms? It also forms. Yes, correct. Yes, most of you have given the answer correct. It is C. It gives you orthopara substituted product. Okay. So this is the correct answer. Orthopara bromotoluene. Correct. Yes. C. C is the correct answer. So next we will see nucleophilic substitution reactions in haloarenes. So see that. So nucleophilic substitution reactions in haloarenes is rare. Okay, why? Because you know benzene is also highly nucleophilic in nature, and the nucleophile, if you want to react on haloarenes, okay, so that is also the nucleophiles are also nucleophilic. Okay, so that is also electron rich. So whenever you have like, so it will repel, it will not form. So if you want to prepare also, if you want to do some nucleophilic substitution reactions on haloarenes, so you have to do some conditions. Okay, so these are some of the reactions with some conditions. So this is chlorobenzene. So if you want to do some nucleophilic substitution reaction, so these are the conditions. So from chlorobenzene, if you react with sodium hydroxide, aqueous sodium hydroxide at 623 Kelvin and 300 atmospheric pressure, it forms phenol and NaCl. Okay, it forms phenol and NaCl. So nucleophilic substitution reaction in haloarenes, it will occur, but there should be some conditions. Okay, so after keeping some conditions only you can do. Now chlorobenzene, if you want to prepare the aniline, okay, from chlorobenzene, so NH3 in the Cu2O, okay, the temperature is 475 and at 60 atmospheric pressure it gives you aniline. So in haloarenes, the nucleophilic substitution reactions are difficult. Okay, hence to carry out the reaction, what drastic conditions are used? So these are the drastic conditions. So to do nucleophilic substitution reaction, it is difficult. Why? Because benzene is nucleophilic rich and nucleophile also are nucleophilic rich. Okay. So because of that, if you want to carry out also, then you have to use very drastic conditions. Then the second point is what? Electron withdrawing groups like NO2, if they are present in orthopara position, then the reactivity of halogens for nucleophilic substitution reaction will increase. So remember this very important point. So whenever you have any electron withdrawing group, what it will do? It will withdraw the electron towards itself. So if it is present in orthopara position, what we will do? The reactivity of halogen for nucleophilic substitution reaction will increase. Okay. So this is the another point you have to keep in mind. So next, based on this, we'll solve some questions. So the compound that reacts fastest with sodium methoxide is? Yes. The compound that reacts fastest with sodium methoxide is, what did I say? So here there are the presence of nitro group. Okay, if the nitro group is present, okay, with respect to halogen group, what it will do? If you have, so if the presence of, so just read this once, then you can go, no, not A, not A. So here you can see, if it is at orthopara position, if nitro group is present at orthopara position, the reactivity of halogens for nucleophilic substitution reaction increases. Yes, correct. Yes. Next. So the correct answer is C. Yes, it is present at orthopara position with respect to the halogen group. Then it is fastest. The reaction rate will be fastest in term of C. Okay, so the C is the correct answer. Good. So chlorination of toluene in the presence of light and heat followed by the treatment with aqueous KOH gives. So C6. So what you are doing? Chlorination on toluene. So toluene is CH3. Okay, in the presence of chlorination means Cl2, then light. Okay, this will give you what? CH3 will be replaced by CH2Cl. One of the hydrogen atom will be replaced by, this is what? Benzyl chloride. Okay, then what you have to do further, you have to treat it with KOH. Okay, further treatment with KOH, what it will yield? What it will yield you? CH2OH, right? This is replaced by OH minus KCl will be the side product. So what is the correct answer? Yes. Yes, yes, correct. Most of them have answered. It is third one. It is D. D, not third one. Fourth one, benzyl alcohol, right? Benzyl alcohol. So it is benzyl alcohol, correct. Which of the following will give yellow precipitate on shaking with an aqueous solution of NaOH followed by acidification with dilute HNO3 and addition of HNO3 solution? Okay. So here the answer is, what is the answer? Can anyone tell? Yes, it is C. Harshita, yes, it is right. It is C. Okay. So what is the answer? So only iodide ion. Okay, remember only iodide ion when it is reacted with silver nitrate, AgNO3. Okay, it gives you yellow PPT. Okay, it gives you yellow PPT of AgI. So when iodide ion is present with AgNO3, what it will give? It will give you yellow PPT of AgI. So in case of A you have iodide? No. So it does not give you any PPT. B, when chloride is chloride is there, what type of PPT it will give? White PPT it will give, right? It will give you a white PPT. And in this also chloride is there, so it will not give any PPT. So the correct answer is C. Okay, C is the correct answer. So Wurtz-Fittig reaction, we have seen Wurtz-Fittig reaction. One will be a alkyl halide, another will be a aryl halide. That in the presence of sodium and dry ether will give you a product. So here we have taken an example. Okay, so this is the Wurtz-Fittig reaction. What do you mean by Fittig reaction? Fittig reaction is what? Two aryl halides. Okay, two aryl halides, when it is reacted with sodium in the presence of dry ether, it gives you aryl compounds. Okay, here example is given as what? Bromobenzene, 2 moles of bromobenzene reacted with sodium in the presence of dry ether gives you what? Biphenyl. Okay, plus 2 NaBr. Grignard reagent. So we have discussed about Grignard reagent also. What is Grignard reagent? They are alkyl or aryl magnesium halides. What is the general formula? It is RMgX. Okay, it is RMgX. So if different halogen atoms are present, the ease of formation of Grignard reagent is, so iodine is more stable than bromine, is more stable than Cl, which is more stable than fluorine. So you know what is the reason for this. Okay, nuclear charge goes on, increases with the increase in the size. Okay, so bromobenzene, when you react it with Mg in the presence of dry ether, you get phenyl magnesium bromide. You get phenyl magnesium bromide. So this is with respect to your aryl halides. Okay, Grignard reagent, it is what? It is RMgX. So Grignard reagent is not prepared in aqueous medium, but prepared in ether medium, because we had discussed this. I think we had discussed this. Yes, it is C. The answer is C, because the reagent, it reacts with water. Yes, Nandish, it is correct. Okay. So we'll go for the, yes, many have answered. It is correct. We'll go for the next question. Which of the following can give a Grignard reagent when reacted with magnesium in dry ether? Yes, which of the following will give you a Grignard reagent? Okay, yes, B is the correct answer. How I'll write the reaction. So C6H5, okay, C6H5Cl, when it is treated with Mg, okay, in the presence of dry ether, it gives you what? C6H5MgCl. Okay, it gives you C6H5MgCl. So it is correct. So the correct answer is C. B. Okay, B is the correct answer. Most of you have answered it right. Most of you have answered it right. Okay, we'll go for the next question. In the following reaction, okay, this is the reactant. The condition is Mg in the presence of ether. It undergoes hydrolysis. So X is the product. So what is the product X? What is the product X? Okay, C6H5, C6H5CH2Br in the presence of Mg. Okay, gives you what? C6H5MgBr. So this on further hydrolysis. C6H5, okay, it undergoes hydrolysis. What it will form? It will form C6H5 here, it will be CH2MgBr. Okay, CH6H5, CH2MgBr. This will be C6H5. Then this will undergo hydrolysis. So this will be removed. So it becomes CH3. The answer is C. Okay, the answer is C. If it undergoes hydrolysis here, it forms what? CH3. So C6H5 CH2MgBr on further hydrolysis will give you C6H5 CH3. Okay, yes, correct. So it is C. So chlorobenzene reacts with Mg in dry ether to give compound A, which further reacts with ethanol to yield. Okay, so it is C6H5Cl in the presence of Mg Grignard reagent. It gives you what? C6H5MgCl. This on further treatment with what? Ethanol. The ethanol is C6H5. Okay, C2H5, C2H5OH, ethanol. This will give you what? C6H6. The correct answer is B, benzene. Okay, correct answer is B, benzene. Cl, C6H5MgCl. Right, after undergoing this is what? C2H5OH with ethanol, it forms benzene. Okay, benzene is the correct answer. It undergoes hydrolysis. Ethanol, it undergoes hydrolysis. Okay. So we'll see the physical properties. So alkyl halides being polar. Okay, alkyl halides is polar. Why? Because there is a presence of. So it is a presence of what? A CX bond, right? X will be your electronegative atom. So because of the presence of alkyl halides, it is a polar bond. Okay, it is insoluble in water as they cannot break hydrogen bonding already existing in water. Because it is a polar bond, okay, it is insoluble in water. Why it is insoluble in water? Because they cannot break the hydrogen bonding. Okay, then greater the molecular mass, stronger will be the van der Waals force of attraction. So as the number of this will increase, so the molecular mass will increase. If the molecular mass will increase, what will happen to van der Waals force of attraction? That will also will be more. What will happen to the boiling point and melting point? So that will be also high. Okay. So for the same alkyl group, Ri, okay, Ri will be more as compared to RBr, then RCl and RF. So on increasing the branching, now when you're talking about branching, okay, what will happen to the surface area? Surface area will decrease. Hence, what will happen to van der Waals force of attraction? That will also decrease. And what will happen to boiling point? Boiling point also decreases. Okay, as you see, if it is a straight chain compound, what will happen? The molecular mass will increase. Thus, what will happen? Melting point, boiling point also will increase. If there is branching, if what will happen? If branching is increased, the surface area will decrease. If surface area is decreased, what will happen to van der Waals force of attraction? It will also decrease. Thus, boiling point also decreases. Then density. So density also iodine. As the iodine mass is more as compared to Br, then compared to Cl and F. So the density will be more. Okay, with respect to this halide. So this is physical properties. So which of the following compounds has the highest boiling point? Yes, which of the following compounds have highest boiling point? We'll solve this question. Which will have, yes, it is B. B is the correct answer, right? Because it is a straight chain compound. The number of carbon atoms are more with respect to first. It is 3. This is second. Then this here they are substituted products. Okay. So it is B, correct. In the group of isomeric alkyl halides, the order of boiling points is, okay. So alkyl halides with branch and more spherical shapes have lower boiling point as a result of their smaller surface size. Thus, primary will be more stable than secondary and then tertiary. So which is the correct answer? Correct answer is D. Okay, D is the correct answer. Yes, the correct answer is D. D is the correct answer. Yes, arrange the following compounds in the increasing order of their density. So if you want to increase, you want to arrange it in the increasing order, then what is the correct answer? Increasing order means from small to big you have to arrange. So here it is A is less than B is less than C and C is less than D. Okay. So it is the increasing order. So A is the correct answer. Yes. So we'll stop for today. Okay, we'll stop it for today. So we have completed the chapter haloalkanes and haloarenes. So please try to solve as much as question as possible. So we'll meet in the next